Alright, hi everyone. Thank you for taking the time to listen to this presentation. Hopefully it doesn't go for too long. However, those who know me in real life know that I don't really shut up about bacteria on a good day, so apologies in advance if it is on the longer side. Unfortunately, I will not be able to discuss the case study that kind of piqued my interest in this organism, and that's because of patient confidentiality and intellect theft and all of those kind of policies. So to show my gratitude to my friends and family for all of the support that I've received, I still wanted to make something that everyone has the opportunity to learn from and listen to. I'm going to try and explain things from the ground up so that everyone kind of can understand what we're looking at, and I hope you enjoy. As a little disclaimer, I've recently been quite sick, and so maybe I sound nasally, and if you don't like that, very sorry, but doing the best I can with what I have. Alrighty, so let's start off with talking about one of my most favourite places in the world, which is the laboratory. For those who don't know me in person, I do work in a laboratory that specialises in working with bacteria and fungi, and I wanted to make a presentation about this bacteria after I stumbled across a really interesting local case regarding a patient who had an infection with this organism that I had never heard of before. So let's take a moment to get acquainted with the bug that we'll be talking about. This organism is known as Capnocytophaga canimorsus, and the name comes from Latin and Greek roots. We've got the genus, which is kind of like a bacteria's last name, and that comes from Latin, and then we've got a species name, which is like a bacteria's first name, and it comes from Greek. So up here is our Latin genus, and down here is our Greek species. When you add all of these components together, you get a name that kind of hints at what kind of bug we're working with. So in this instance, it's a bacteria that's associated with dog bites who likes to eat carbon. Naming for bacteria and other pathogens isn't always so straightforward. In fact, sometimes names just straight up suck. They're always changing, and bacteria are constantly getting moved into new families, so it can be a little bit tricky to keep track of who's who. An example is Enterobacter orogenies is now Klebsiella orogenies, and I personally know that I will never, ever forgive the taxonomists for changing Candida krusei, or Krusei, depending on how you want to pronounce it, to Pichia kudryavzivivi. Look, I can't say or spell that new name, so I'm personally quite offended. Long story short, we don't like the taxonomists over here. I mean, we respect the hard work that they do, but we don't like them. Thank you for doing such a good job, taxonomists, but also we're not friends. Getting into the nitty-gritty of the laboratory ID of this organism, what we can see is we've got a gram-negative bacillus, which means that it's going to stain pink when a gram stain is done, and it is a long rod-shaped bacteria, which essentially means it's not circular. We'll take a look at gram-positive and gram-negative organisms on the next slide to make it a little bit more clear. But for this bug, what we know is it's gram-negative. This organism is fusiform in shape, and essentially that's just a fancy way of saying that it is long and slender with tapered ends. So in the microbiology world, that kind of hints at an organism being an anaerobe based on its microscopy. This bug is about 3 to 6 microns in length, which means it's quite large. For comparison, I have put a picture of E. coli down here, and for reference that is about 2 microns in length. So comparing the two, E. coli looks very short and chunky. Capnocytophaga canimorsus is catalase and oxidase positive, and we'll look at what this means in a moment, but it is a big deal because it's what separates the human species of Capnocytophaga from the animal, because the human species are oxidase and catalase negative. This organism can grow with or without oxygen. Some bacteria are quite picky about which environments they're going to grow in. Some love oxygen, and we call these obligate aerobes. Some hate it, and we call them obligate anaerobes, but most don't really have a preference, and the ones that don't care we call facultative anaerobes. While this organism is a facultative anaerobe, it does have a documented preference of high levels of carbon dioxide. In fact, it likes much higher than most bugs, looking at a requirement for about 5 to 10%, leaning more towards that 10%, and so we term this as being capnophilic. This organism is quite slow growing, and the strains that I was working with last year were taking about 2 to 3 days to see any decent growth. Depending on the bug, sometimes we can see some growth in under a day, so to put it in perspective, it is very, very slow growing. As promised, I've got some examples of gram-positive and gram-negative bacteria. I won't get too deep into the science of it all, but it has to do with the cell wall structure of the organism as to whether or not it will stain this purple colour as a gram-positive or a pink colour as a gram-negative. And I do want to point out that for some reason Pseudomonas aeruginosa has been lumped in with a gram-positive bacteria, which is wrong. It should be over here with the pink ones. If you want to get to know me a little bit better, some of my favourite gram-positives include Streptococcus pyogenes, Bacillus anthracis, and Listeria monocytogenes. And some of my favourite gram-negatives include Neisseria gonorrhea, Pseudomonas aeruginosa, and Burkholderia pseudomallii. So if you don't like to learn from cartoons, I do have some real-world examples here. Depending on the shape and the size and the way that a bacteria will present itself in a gram stain, it kind of gives us a hint as to who we might be looking at. So if you want to compare these guys up here, on first glance they might look very similar, but they do have their differences and they can kind of hint as to who we might be looking at specifically. So looking at this left one here, you can see that there's these little tetrad formations happening, and when multiple tetrads sit together, it starts to form grape-like clusters, which is something that morphologically Staphylococcus aureus likes to do. Whereas if you jump over here, you'll see that they're in pairs, which you can also kind of see over here happening, but there are no tetrads being formed. Additionally, you'll see that they have these little zones of clearing around the bacteria, which is known as a capsule, and it's something that Staph aureus isn't known as having in a gram stain, whereas Streptococcus pneumoniae is. So, first glance, they're both gram-positive cocci, however, morphologically in a gram stain they're a little bit different. Same but diff. Down here we've got 2 pictures of gram-positive bacilli, except you can see in this bacillus gram stain, the bacillus is kind of like hanging out in this chain structure, whereas the Clostridium species, they're all singles. Additionally, when you look at the ends of these guys, there's nothing, whereas over here, there's these little circular structures known as a subterminal spore. So again, that kind of helps us distinguish a bacillus species from a Clostridium species. Over here, interestingly, sometimes you can't really tell a gonorrhea from a meningo via a gram stain, which is why I haven't put them together because they kind of look a little bit similar. But what we're looking at here is a gram-negative intracellular diplococcus, which is a lot of words, but it does tell you everything you need to know about the bug. So we've got a gram-negative, which means it's staining pink. We've got a gram-negative intracellular, which means it likes to hang out in the white blood cells over here, as you can see. We've got a gram-negative intracellular diplococcus, so like strep pneumo, gonorrhea also likes to hang out in pairs, like imagine little schoolgirls holding hands, walking around like everywhere together, but obviously 2 very different pictures. You can see that it looks like they've been phagocytosed over here, except not necessarily. What you can see over here is the strep pneumo sitting on top of the white blood cell, whereas here they've actually been eaten by the white blood cells, so gram-negative intracellular diplococcus. Moving down here, we've got a gram-negative bacillus, and I wanted to include this one because this one's one of my favourites as well. And it does something very cool, which is called a safety pin morphology. So it's bipolar staining, meaning that the ends here are a little bit darker and the inside is a little bit more transparent, but morphologically that's something that kind of red flags a potential Burkholderia pseudomallii, which is actually a very nasty bug. Taking a look at what we call bench testing, we can use chemistry to kind of figure out who we're looking at as a really rapid form of ID. The only downside is that we need the organism to have actually grown up to at least one colony before we can start to do our bench testing. The catalase is a bubbles-based reaction. We're looking at the change of hydrogen peroxide into water and hydrogen gas, and that's over here. So you can see the negative, there are no bubbles forming, but over here we've got that hydrogen gas being produced and water. The oxidase bench test is a colour reaction, and it's actually kind of complicated, but the easiest way to describe it is we're looking at oxygen being converted into water with the assistance of an enzyme, and that's our image here. So we've got a nice purple colour for a positive, and no change is a negative. You can kind of see the colour here, but really what we're looking for is a very rapid reaction. If it takes time for the colour to develop, we still call that negative. Bench testing is a easy, relatively fast and relatively inexpensive way to go. It's very good for small laboratories that don't have fancy equipment. We have these machines in our tertiary laboratories that use lasers to figure out who a bug is, basically by exploding them into tiny little pieces and analysing their proteins, which is really cool, but it's also really expensive. So bench testing is essentially our bacteriology roots, and we need to respect our bread and butter. Of note though, sometimes the results that we achieve from our bench test isn't exactly what we're anticipating. Some bacteria do deviate from that game plan, so it's always good to employ a couple bench tests and look at the whole picture together. A really good example of this is one of my Capnocytophaga canimorsus strains was oxidase negative when in theory it should have been positive. So it should have actually looked purple like this, but I was getting a result like this. I believe that potentially either it was just a variant strain or freezing this sample for over 12 months kind of impacted the biochemistry of the organism. So we would use, for example, maybe the gram stain and the catalase and the coagulase to figure out what kind of gram positive we're working with, or a gram stain and an oxidase to figure out what kind of gram negative we're working with. But let's get back to our bug. So here's what we see in the laboratory as far as growth. In bacteriology, we use what's called an agar plate, which is essentially a jelly-like medium to grow our bacteria, and we can add things to these plates or take them away to assist us in growing only what we want without the overgrowth of things in the background. There are so many different types of agar plates commercially available that you can essentially grow almost anything that you're interested in. On the left here we have a red blood agar plate in which we use sheep or horse blood as a base, and this is very nutritious, and bacteria love to munch on the red blood cells as their source of nutrients. On the right hand side here we can see a brown chocolate agar plate. Unfortunately this isn't as delicious as real chocolate, but this agar has been heated, so essentially we're working with cooked red blood cells. In the heating process they break down, and so the bacteria don't have to work as hard for their snacks. And so this plate is super nutritious, which is great for growing bacteria that kind of act like fussy toddlers, such as Haemophilus species and Neisseria species. This organism doesn't grow very well on MacConkey agar, which is a selective agar plate that we try and use to isolate our gram-negative organisms with. And if you remember, Capnocytophaga is a gram-negative organism, so it's always good to note that not all gram-negatives are a fan of MacConkey. Other examples include Neisseria gonorrhea, Neisseria meningitis, and Pasteurella multicida. This organism does not produce enzymes called hemolysins that primarily break down red blood cells and form a zone around colonies, so we can see that this red goes all the way up to the agar. Oh my gosh, wrong word again. All the way up to the colony. There's no zone of clearing, so we call this gamma hemolysis. And the colonies, when they do grow in their clusters, grow with an interesting morphology, so they have a strange irregular shape with these little finger-like projections, which is quite unique. But when they are isolated in the form of a single colony, They tend to be punctiform, which is a fancy way of saying pinpoint, especially early on in the incubation process, so around that 24 to 48 hour mark. This bacteria is capable of movement via gliding motility, and the easiest way to picture that in your mind is just imagine a little bacteria on a skateboard. So it's a very smooth and linear movement. It seems like this bacteria could be a little bit more common than we think. It is very difficult to grow routinely, and you do need to tailor your investigations if you want to find it, but the source is quite common. Almost everyone has or has at least had one in their lifetime, and do stay tuned for that because we'll discuss that next. So you have to ask why. The fact of the matter is we need a longer incubation, we need more carbon dioxide, and this bacteria is a lot happier on a brown chocolate agar plate than it is on that red blood agar plate, so careful plate selection when processing a sample is required. How does this impact the treatment of a patient though? Luckily it doesn't. This bug is very easily treated, and I will discuss that in a little bit, which leaves the question of how does this impact our data collection? As it would turn out, it does impact it quite a bit. If we want accurate, statistically significant data about how often this organism is causing infection, we'd need to put a lot of effort into trying to culture it. This isn't really worth it clinically due to the easy nature of treatment for this organism, but for research purposes, I believe that the effort, the time, manpower, cost of culture, etc. would be worth it. One of the sources that I read stated that 500 cases of this organism have been documented worldwide, but I believe that that is a gross underestimate. As far as what the laboratory needs to think about for this bug, are we incubating our plates long enough and in the right atmosphere? So for example, if we're incubating our plates for 48 hours in 6% carbon dioxide, we're likely to not grow this bug. But if we incubate for 48 to 72 hours in 10% carbon dioxide, our chances are a lot better. In addition, if we do manage to grow it, are we required to identify it? I've been able to grow this bacteria without carbon dioxide in anaerobic conditions, which again, no oxygen, and that took 2 to 3 days, so we might get lucky if the anaerobic plates are set up for these samples. But if a laboratory procedure for non-sterile sites states that you don't have to identify anaerobes, this bacteria might be growing and we just won't give it a name. One thing to note is that swabs, which are non-sterile, the incidence of capnocytophaga being isolated from these samples is quite low, but for sterile sites like blood and cerebrospinal fluid, we should hopefully be able to catch this bacteria on our anaerobic plates. And for example, if a laboratory has a procedure in which you need to identify your anaerobes from your sterile sites, then we might have a chance of identifying this bug by name. Something for our clinical teams to think about is, did we accidentally treat this bacteria before we collected our samples? And I guess accidentally is the wrong term. You do want to be treating your patients, but hospital protocols are typically in support of collecting samples before the administration of antibiotics for culture. And so the idea of that is we want to keep the yield of our infectious organisms high, but sometimes that just isn't always the case. It's not actually unusual for the laboratory to notice antibiotic-affected bacteria and gram stains. And additionally, knowledge is power, especially for weird organisms such as this one. If the clinical team or the laboratory staff don't know what to look for with regards to a capnocytophaga, it could very easily fly under the radar. So let's discuss where we find this bacteria the most often. If you have a pet nearby, you might find yourself starting to side-eye them just a little bit. Capnocytophaga canimorsus is documented as being canine and feline normal oral flora. So what we're saying when we say that is that this bug is commonly found in the mouth of our beloved pets. We can catch it from our fluffy friends from licks, bites, and even simple close proximity. And I want to ask the question of how many of you sleep with a pet on or in your bed, maybe even near your head. Even after learning about this bacteria, I will not stop my cat from snuggling me. It was first formally mentioned in the scientific literature in 1976, so it's still relatively new in the scheme of things. However, it has been 48 years and we still have unanswered questions and very little data regarding this bacteria. A Netherlands study showed that anywhere between 0.5 to 0.7 in every million people were culturing this organism from their samples. Again, I'd like to call into question the validity of that data, and it's likely that we have been missing cases based on what we just had discussed before. Most clinicians and laboratory staff won't even think about this bacteria in their differential diagnosis unless there is a clinical history regarding an animal mentioned, so things especially like dog bites and cat bites. So now that we've looked at the laboratory and the source, let's talk about the patient and have a look at what happens if you do catch this infection. There are a couple risk factors to keep in mind for this bug. If you're unfamiliar, a risk factor is something that makes you more prone to catching the organism. First and foremost, our number one risk factor for practically every bug out there is immunocompromisation. This bacteria isn't so bad in a healthy person because they have an efficient immune system to fight off the bacteria. However, immunocompromised patients have a hindered immune system, which leaves them more susceptible to infection. Some examples of immunocompromisation include cancer patients, transplant patients, HIV/AIDS patients, patients with autoimmune disorders such as SLE, rheumatoid arthritis, and Crohn's disease, patients on high-dose corticosteroids, and the elderly and our newborns. Next, we have asplenia or hyposplenism. This means a patient that does not have a spleen, or they have a spleen that is not functioning at 100%. Your spleen is an organ that is basically one big biological filter. It removes cellular waste and old cells and makes and activates your immune cells. In asplenic or hyposplenic patients, we see a decrease in antibody production and a decrease in opsonophagocytosis. That is a fancy way of saying that molecules and pathogens that are covered in antibodies that immune cells would usually snack on aren't being removed from the body. The next risk factor is liver cirrhosis. We see a decrease in innate immune protein production, which results in a lack of effective immune response. Lastly, excessive alcohol consumption is also a risk factor for Capnocytophaga canimorsus. Excessive alcohol consumption can lead to liver cirrhosis. Additionally, excessive alcohol consumption can lead to a decrease in superoxide production and a decrease in neutrophil elastase activity. So try not to be too much of a party animal the next time you go out, because as it turns out, you end up giving your immune system a hangover too. Let's take a look at how capnocanimorsus can cause trouble in the body. We can start to see signs of infection anywhere between 1 to 8 days post-exposure, and this organism takes around 7 days on average to incubate and grow into enough numbers to start to cause real issues. Some of the clinical manifestations include sepsis, which is the reaction of the body to a bacteremia, which is an infection of the blood, in which your organs and tissues take damage while your immune system tries to fight the infection. The mortality rate of sepsis is approximately 30%, and Capnocytophaga canimorsus has its own documented mortality rate of 20 to 30%, which means that 1 in every 3 people with this bacteria in their blood will unfortunately pass away. In addition, Capnocanimorsus can also cause a condition known as fulminant sepsis, which is a really bad form of sepsis that comes on fast and is extremely difficult to treat in time. Examples of the symptoms of sepsis include tachycardia, which is an increased heart rate, hypertension, which is a low blood pressure, the inability to regulate body temperature, confusion, and a rash. Another clinical manifestation includes meningitis. This is the infection of the meninges, which are the tissues that surround your brain. This has a mortality rate of 5%. Additionally, we have cellulitis, which is the infection of your skin and the surrounding tissues. This has a mortality rate of less than 1%, but we can see another condition known as purpura fulminans, And to put it simply, it's when your blood vessels get blocked up, the blood stops moving around your body, which leads to tissue death, and your blood vessels eventually break down and blood starts to pool into your surrounding tissues. Something interesting, in my opinion, is that our isolation rate actually corresponds with the mortality rate. We're most likely to isolate this organism from blood, and as I mentioned, this has a mortality of 30%. Next, we're likely to isolate it from cerebrospinal fluid, and that has a mortality of 5%. And then lastly, we're least likely to isolate it from our wound swabs, and that had a documented mortality rate of less than 1%. And for my final slide, let's look at the treatment for this bug. In front of you is a list of some fancy and intimidatingly long names, but they're all just antibiotics. You might recognize some of the names on this list, having taken them before. The good news is that most of the drugs from this list are in the left-hand will work column, meaning that Capnocytophaga canimorsus is what we would call a sensitive organism. Now, that doesn't mean that this Capnocanimorsus cries very easily like someone I know. What it means is that it is very easy to treat, which is fantastic considering that a current stressor in the world of microbiology is that we are slowly moving into the realm of an antimicrobial resistance era. Some of the drugs that are in the middle might work column will be a roll of the dice as to whether or not these drugs will work. It will depend on the strain of Capnocytophaga canimorsus you are trying to treat. The antibiotics in the won't work column on the right are what we would call resistant, which is not good. We want less drugs on this right-hand side and more drugs in the left-hand will work side. Of note, depending on what literature you read, if that's what you do for fun, the aminoglycosides have been reported as being either variable or resistant, so might work or won't work, and that's what I was referring to when I said that we've known about this bug for 48 years and we still have some gaps in knowledge. Hopefully, this will be cleared in the future. Some strains of this bacteria have been documented as producing enzymes called beta-lactamase, which is also not good because it allows this organism to become more resistant to drugs. To avoid more drugs moving over to the right-hand side of the slide, i.e. becoming more resistant, clinicians need to be careful of overprescription of antibiotics. Additionally, they need to be able to appropriately prescribe antibiotics, meaning that we don't want them prescribing penicillin if their patient already has a penicillin-resistant organism. And patients need to always finish their antibiotics when they're prescribed. If you don't follow the course, you can potentially allow the selection of resistant mutants, and if you don't kill off all the bugs, they can just replicate and reinfect you again. Of course, credit where credit is due, these are my references. If you have any questions, I'm just a text message away. I'm always happy to talk about bacteria. And on a finishing note, thank you so much for your attention, thank you for tuning in, and again, thank you for all of the support that I've received while I've been working on this organism. That's a picture of my sister's dog, Millie, and I laugh every time I look at it.